Okay, so let's start this lecture on approximating the value function. So last time I talked about a few methods, including approximate value iteration for computation of the value function using a bunch of data. So the setting was in the batch RL, so we have a data, and then we want to approximate the value function, either value function of policy or optimal value function. And approximate value iteration or fitted Q iteration or fitted value iteration are kind of two methods or one method for doing that. And there are a lot of varieties of it. It's kind of like a family of methods, depending on how exactly you choose this function space. You can choose it linear function space, you can choose it decision trees, or you can use a neural network to represent it. So actually one of the earliest kind of success stories of these type of methods was using something like, they were random forests, essentially, an ensemble of decision trees. So that performed very well compared to many other methods. But then later, people moved to using deep neural networks. And they perform very well, of course. Okay, so I'm going to continue that path, like still talking about batch methods, and talk about this Bellman residual minimization, and talk about how we can get a sample-based method or data-based method out of this Bellman residual minimization, which we saw before in the form of population loss, minimization of some population loss function. So what we had was essentially this equation or this optimization, which we were minimizing Q in some function space when minimizing of this Bellman error. So Q minus T pi Q. So here we can talk about, say, L2 norm with respect to distribution mu. So this is some distribution that we choose. And then if we could find it, then that would be the minimizer of the Bellman error. And I think we had some results like upper bounds showing that if you minimize the Bellman error, then the quality of the function, the Q function, value function that we find, how is it related to V of pi? So we could, something like this would upper bound some quantity like Q minus Q pi. And we talked about supremum norm type of upper bounds, but also I think we talked about the case with station distribution of policy pi. So that's basically, so there's a constant to it. So that was a population version. Now what we want to do is find a kind of empirical version of it. So that's a good question. No, I did not upload these slides. Maybe I can upload it if that's okay. So now we want to talk the empirical version of it. And the idea here is that we just use data in order to change this kind of norm, which is with respect to distribution mu with data. So what's the form of data? This is as before. So we have xi, ai, ri, and xi prime coming from next states. And also say we have the assumption that xi comes from distribution mu. So this is the distribution of xi. And then if we do that, basically what we are doing is that we are replacing this integration with respect to w mu with integration with respect to this empirical distribution or empirical measure, which is defined based on this data. And the other step that we are using data is that we substitute T pi Q with its empirical version. So empirical Bellman operator applied to Q. So how does it look like? So this norm becomes this summation. So it would be 1 over n of summation over all data points of Q of xi ai minus T hat pi of Q xi ai. And then we had also this notation that we can write it in the norm notation, but just add 2 and dn in order to mention that this is the distribution Another similar notation that sometimes we may use is that just use mu(n), 2m mu(n) instead. Okay. So do you remember what was this t hat pi was? Or what would be this form of t hat pi of q? So anyone on chat, maybe you can add it.
Just the Monte Carlo estimation of.
Is it going to be Monte Carlo estimation or something else? Like Monte Carlo estimation, like expanding it until the end of episode, you mean?
Oh no, one step.
It will be one step, yes. So any guess? Like if it's one step, so yes, that is one step. So it's kind of one step. So you see, this is a Bellman operator, but it's empirical Bellman operator. So it should be similar to Bellman operator, but we just replace integration of our next step with just one single sample. Any guess? Okay, there's one thing in the chat. Average over actions at a of I plus 1. Not exactly, no. Let's see. So let's see if we can find it. Okay, yes, so it's here. So in approximate value iteration, we had it earlier, actually, I think the previous chapter, but this is empirical Bellman operator. Applied to a Q, this means that we have, say, t hat of pi of Q at x and a. So it wouldn't be an I. So it would be the reward that we get plus gamma times Q times x prime and pi of x prime. So that would be the form that we have. So here we would get, so this would essentially be Ri plus gamma times Q of xi and pi of xi, I think. So I made a mistake. What is the mistake here? Okay, yes, exactly. So it should be xi prime because it's at the next state, yes. So that's right. So that would be it. So that would be our objective. So now you have a Q and you're parameterizing Q in some way using your neural network, your linear function approximate or whatever. And then you have this loss function, and then you can try to minimize it. So this is kind of, it's not very difficult. Like if essentially you need to compute, like Q has some parameters, maybe W, that defines, that parameterizes it. That would be parameters of, say, neural network. Now first you evaluate Q at XIAI, one data point, and then minus reward, minus gamma times Q at xi prime and pi of xi prime, so at the next state. And then try to compute it. You can compute the gradient of it and then backpropagate it if you use a neural network to compute the move in the direction of opposite direction of gradient to gradient descent. So if you compare it with, okay, so there's a question. Okay, so if pi is a distribution of our actions, so because that's a good point. So then we can have summation of our actions according to policy pi. So I think what you earlier said, average over actions, that makes sense. So it would be here, instead of this term, we would have something like summation over action of pi of action xi prime of q of xi prime and a prime. So instead of this term. So that would be the change.
So this has been confusing me a little bit, because if you're in a continuous action space, then to estimate that expectation, you have to sort of run many more simulations to collect samples, I suppose. So how do people deal with this?
Right. So that's a good point. I mean, I can say two answers. If you want, if pi is in this form that we have here, and we have summation, then it becomes integration if it is continuous action. So one way to do it, so that's one of the difficulties of working with continuous actions. But one other possibility is that you just take a sample from that action. So if you can sample from that policy easily, then your sample would be an unbiased estimate of this whole term. So even if you have, say, action, we call it x prime, that is coming from this distribution xi prime, then if you write your q at xi prime and a prime, and if you take expectation of it, condition on, say, xi prime, that would be exactly this summation or integral, if it is an integral. So you can have a single sample unbiased estimate of that quantity.
Okay, thank you.
Right. I guess the point here is just doing a Monte Carlo sampling of size 1, because anyway, for the next stage, we are also like doing the sampling process, not integrating over all possible next states, which is exactly what we do in temporal difference learning, right?
Yes, exactly. Like it is one step. Like even at the next state, we are not having samples over all possible x primes, right? It is only one sample from it. So we can have one sample from xi prime and one sample from ai prime, and both of them would together makes an unbiased estimate of this, make t hat pi of q an unbiased estimate of tq. So which is, I think, what I had somewhere. Okay, maybe. Okay, yes, here. So this is essentially this statement that if we have a randomness here, that's if we take expectation, we integrate it, it would be the same as TQ. So here the way I wrote it was for single 1 pi, but you could also write it for one sample from pi if pi is not deterministic, and nothing would change really. So all is good, but okay, so one thing, if you compare it with approximate value iteration or fitted Q iteration, you see that there is only one Q appearing in approximate value iteration. So what we had, the optimization would be Q minus T hat pi of QK for fitted Q, AVI, or fitted Q iteration. So the difference here is that we have a K here, but we don't have a K. So in some sense, both terms in Bellman residual minimization are both of them are Q. But for approximate value iteration, only one of them is Q, and the other is fixed. It's a QK, so it is not a function of current Q that we are optimizing. Is this clear? I'm getting a few nods. And this is an issue, actually. This causes an issue because the minimizers of, say, the true Bellman error, Q minus T pi Q, and I'm even not talking about data over, like the distribution over X is coming from mu. And the minimizer of the one that has T hat, which we are replacing one sample, again with the same distribution, they are not necessarily the same if the MDP is stochastic. So this means that the goal was to minimize this, like the population version when we started, I think last lecture or the lecture before. We want to minimize this because minimizing this Bellman error has nice properties. But if we are minimizing some other quantity with a different minimizer, that's not necessarily getting us what we wanted. So let's see why this is the case. And when we go through it, it becomes more clear what is the difference between them. So to compute it, okay, so to see this, we compute just for one state action pair. So I call Z equal to X and A just to shorten the notation. So I'm computing the squared error of Q minus T hat pi of Q, both evaluated at Z, conditioned on Z. So this is by conditioning on Z, I'm essentially saying that Z is not random. So I'm fixing state and action, one state and action, but the only randomness is coming from the next state, which is because we had in this T hat, we had reward plus gamma times Q of next state. So there is a randomness at next state. So essentially I'm saying that I'm at Z. So there is a randomness going to X primes. So I just want to see what is this randomness. And based on that randomness, but I don't want to see what's randomness. What I want to see, what is the effect of this randomness on this objective. So this is going to be like this, that we had similar calculations before for AVI. So what I do is that I just write this expectation, Q minus T hat pi of Q. I subtract and add T pi Q. So this is the true Bellman operator applied to Q. So we have these two terms are added and subtracted, so they don't change the summation. And these are the same as before. And now I just take this to the power of 2 and separate terms. So one term would be the first two terms to the power of 2. The other would be the second two terms to the power of 2. And the other would be the two times inner product of them. So if we do that, so we get expectation of Q of Z minus T pi of Q of Z squared or condition on Z. The other one is T pi of Q minus T hat pi of Q. So the difference is just one of them has hat. It's an empirical version, empirical Bellman operator. The other is not. And then the last term is inner product of these two terms. So we can argue as before that inner product is 0. And the reason is that, okay, so we can compute these things. So inner product, it's conditioned on Z. So the things that are function of Z, and there is no randomness, so by function is that you can compute the value in a deterministic way, comes out of the expectation. So the inner product becomes Q minus T pi Q, this whole thing, times, I could take both of them out of the expectation because Q of Z, there is no randomness condition on Z. And T pi of Q at Z, there is no randomness condition on Z. The same is for this t pi of q term in the second part of that inner product, minus expectation of t hat of pi of q evaluated at z condition on z. So this one, there is some randomness beyond z in this t pi hats, which is basically because we have randomness over the next state. So even if I give you z, you don't know, there would be some randomness of what it would be the next x prime would essentially be. But this expectation, as I showed before, is exactly equal to t pi q evaluated at z, because t hat pi was an unbiased estimate of t pi of q. So these terms would become the same. So we see that we have t pi q minus t pi q. So this whole term would be 0. So this inner product, the whole inner product becomes 0. So what I get here is expectation of q minus t hat pi of q, condition on z, would be expectation of this q minus t pi of q. And actually, we don't need this expectation because there is no randomness here. So I mean, this is not incorrect, but I can remove it. So there's no expectation, just squared value of it, plus the other term. What was the other term? The other term was expectation of t pi q minus t hat pi of q. So t pi of q is like it was expectation of t hat pi of q. So this whole term essentially becomes a variance term. So this becomes variance of t pi hat of q evaluated at z. Okay? Is there any questions so far? I mean, you have to go through it to fully understand it, but is there any clarification needed?
So this variance term is exactly the thing that depends on how many samples you have, right, for the next state action.
Right. Yes. But just imagine, here I assume that there is only one next state from data. Like here, the assumption was there is for each xi there is only one xi prime. If we had multiple next state from each single xi, then we could define this empirical Bellman operator a little bit differently. And in that case, the variance would be depending on how many next state I have from each single state xi.
Right. Yeah. Yeah. Sorry, I might have misspoken. I was trying to talk about actions, next actions.
Okay. So if you have next action, yes. Again, I mean, if you have multiple next action, you can reduce that variance or part of that variance. If you take multiple next actions, yes. So there would be essentially this variance would depend on part of it comes from the next states, going from xi to xi prime, and the other is that how many ai prime we would have.
Right, makes sense. Thank you.
So, but let's see how it looks like. So, so this was essentially objective at one single z. So if you take integral over the whole z's, what we get is essentially the loss function that we care about. So here this expectation is over z's, over state actions, according to some distribution, maybe distribution mu, and we are trying to minimize it. So this term is what is minimized by empirical Bellman residual minimization. But only considering this effect of t hats, not the data point over x's and a's. So the decomposition that we had was essentially this, that this expectation would become Q minus T pi Q plus expectation over Z of variance of T hat Q, not K. So this was exactly what we got here. So there is no K here. So this variance term plus this Bellman error term, essentially. So these two terms, so what we are minimizing has this term 1 and term 2, but this is in general would be different from Q minus T of Q, right? Because of this second term.
So that second term, Professor, I just want to make sure I'm not thinking about it wrong. The variance, when like calculating the variance, is this, correct me if I'm wrong, it's kind of like the formula where like E of x squared is equal to E of x squared plus the variance of x kind of thing, where, you know, if you take, for example, if we go to the back of the last slide, or 2 slides ago, actually. Yeah, so that term, if you take the expected value of that term, it just becomes T pi minus T pi because of the unbiased estimate, right? And then you're left with the variance.
Right, so this is similar, I guess, to variance that you're mentioning. But there is one important point here. The important point is that the variance depends on Q here.
Mm-hmm.
So this is kind of the important part, because if the variance was not a function of Q, so it would not change the optimization. So essentially, say I have kind of more, I'm arguing of some function of, say, some loss function, which depends on f, plus some sigma square, some constant, which is not a function of f. So this would be the same as arguing of that loss function f. So here the loss function is like the Bellman error. But this variance, the difference here is that this variance
depends on Q.
Depends on Q, which means that if I search in the function space to find the minimizer of these two terms, depending on which point I'm choosing, I get different effects of variance. Yeah. And that is the issue, actually. So I think in the next slide, I'm going to kind of expand this variance, but the kind of the general conclusion or the basic kind of result here is that if we have a stochastic dynamical system, the variance term would be non-zero. If it is deterministic, the variance would be 0, because single sample at the next state would be the same as any other sample. Like the distribution always lands to the next single next state. So if it's deterministic, we are okay. But if it's not deterministic, it is non-zero, and it affects the minimizer. So we are essentially finding a solution by using T hat instead of T. If it's a stochastic dynamical system, we obtain a solution that is not the same as the minimizer of the Bellman error. So this was the minimizer of the Bellman error. This is what we are getting here. And these two things are not, for stochastic dynamical systems, are not the same. The effect is that we find something else, which may not be necessarily good. So just let's look at this variance a little bit closer. So I assume that the reward is deterministic. So Ri, the reward that I get for ith data point, is R of xi ai. So, and R is just like a function of xi and ai. So there is nothing random on this if we know xi and ai. So this is just to simplify it. So if we do this, we write the variance of t hat pi of q condition on z. So I just expand both terms. So the variance of it was, So essentially, I'm writing this term. Different color. So I'm writing this term, which is the variance. And I expand the definition of t and t hat. So for t hat, I'm getting reward plus gamma xi prime pi of xi prime. So that's the first term. And for the other part, the t q part, this would be its expectation, of course. So we have reward again, but instead of just one sample, we have this whole integral over the next states. So the reward part cancels because I assume that rewards are deterministic. So what I get is just this gamma times q minus gamma times this expectation of q at the next state. So if I take the gamma discount factor out, so I get gamma squared here plus expectation of q x prime pi of x prime minus integral of q at the next state. So this would be also, this would be essentially q of x prime pi of x prime condition on z essentially. So this is the expectation of this term, which makes the whole thing like sigma squared the variance of q of x prime pi of x prime, okay, condition, oops, condition on z. So that's what we get, and which I'm writing here. So this is the value, but I didn't write it here. So, but that's the kind of what we get. The variance of the t hat pi is essentially gamma squared times variance of q at the next state. And the variance the randomness comes from the transition of, it comes from the x primes, the next state that we get, starting from point z. So there were some questions.
How did you get that second term, Professor?
Which one?
The one after the minus.
This one?
Yeah, it might be a stupid question. Just no, the above it.
Above this? Okay, so two ways. Okay, so because the variance is, I have two answers. The first answer is that that was the term that I have here, right? So actually I wrote it this form, like I had t hat pi of q minus t pi of q here.
Okay.
So I just wrote, so that integral part is coming from t pi of q.
You just wrote it out, yeah.
Write it down. So I guess the question is that why this is variance? Because
that was my original question earlier. I thought that maybe it's just like coming from the formula where, you know,
right, yes, it comes from that. Okay, so maybe I misunderstood your question, but yeah, so variance of something, or let's write it like this. If you have a random variable, let's call it x, but not related to state here. And the whole thing squared, this would be the variance of x. So because variance is essentially the difference between some random variable to its mean or expectation squared. So that would be the variance. Now I guess the question is that, so here I'm equating, let's use another color. So this x plays the role of this term, and this expectation of x plays the role of T pi Q. And why is that? Because expectation of, say, T pi Q, Z condition on Z, that is T pi Q of Z. So expectation of the empirical Bellman operator applied to Q is the same as the Bellman operator applied to Q. So this makes it this term that I have here equal to this term, so I can replace it with its expectation, and then it looks like this equation that I have here, and it's becoming a bit like spaghetti, but still, hopefully it's not too obscure. And then we get this, that this is variance. And in the next slide, I'm replacing that second term that I have here with this variance term as a kind of a shorter notation, so that it would be shorter when I'm writing it here. But then when I expand it here, so I again put the definition of variance and write both terms, like this would be T hat pi of Q, this would be T pi of Q, which is the expectation of T hat pi. Okay, right. Okay, I guess that's, is this clear? More or less?
Yeah, thank you.
Okay, perfect. So we have this variance term, which is essentially the variance of Q at the next state. And we know that this because in optimization, in that optimization, because the variance depends on Q, it changes the minimum of the minimum function Q that we would find if the dynamics is stochastic. So let's see what it's kind of basically a few points. Here is that, okay, so this is the variance of Q at the next state X prime. So having this variance term acts like a penalty when we put it in an optimization problem. So it encourages finding Q that has a small next state variance. So what does it mean? So if Q is constant, if we find a constant Q, this term would be 0. So, and since that term is non-negative, that's the minimum of it. So the best Q to minimize this variance term in this optimization problem, so this optimization problem, is to find, if we only had the second term, it would be find a Q that is constant, and that would be the minimum. But of course, we have the first term, which is the Bellman error, which makes it make a constant function not a possible solution, at least in most cases. So if Q is constant, this term would be 0. And you can argue that if Q is varying slowly as a function of states X, so essentially you have a Q that is kind of like this space of next states or states, if Q is kind of changing very, very slowly, so it's kind of almost like constant, this variance term would be small. So this is the penalty term is encouraging. So you can say that it's encouraging finding a Q that is smooth in some sense over states or state action. But then this, I mean, usually in machine learning, we say that, okay, it's good to have, let's say, a regularizer to enforce the optimization to find smoother functions. So smoothness is not necessarily a bad thing. Sometimes we design a regularizer to control the amount of smoothness in order to, say, avoid overfitting. But this is not the type of smoothness because we don't have any control over it. So there is no regularization parameter that we can change in order to make the function smoother or less smooth. And if you recall from your course on machine learning, that regularization parameter should depends essentially on like how many data points you have. If you have a lot of data points, if you have only a few data points, usually regularize more to avoid overfitting. But if you have a lot of data points, your regularization coefficient should go to 0, essentially, generally speaking. But here we don't have control over it, so there's no hyperparameter to control that variance term. And this is essentially variance that is imposed by biasness of the objective function. So yeah, so that's essentially the idea. Like Bellman residual minimization in the population case, when you had actual distribution, makes sense. That's a good idea. But when we go to empirical version of it, you want to use data in order to estimate it, the result would be biased loss function, which may change your solution in a way that is not intended. So that's kind of not desirable. And one other thing is that there is a solution for it. There's a way to kind of subtract that extra variance term, like somehow estimate it and subtract it, and makes the procedure reasonable. So it's called modified Bellman residual minimization. So it comes with some theoretical guarantees. But the form that I explained doesn't have that property, and it would be biased. Okay, so let's see if there was a question, I think. Okay, so that was a chat. That's okay. Yeah, so let's have a break, and then the goal is to finish today. I think it shouldn't be too difficult. Maybe we have a break now. It's like almost 2:05. Maybe we start at 2:10 in 5 minutes almost. Okay, so let's continue. Here, in the previous lecture, we talked about several value approaches to approximate value function. One of them was essentially using Bellman residual minimization, minimize the Bellman error. And I talked about how to do it when we have empirical data. And as we just saw, this is not a very good idea. Another approach that we saw was value iteration or approximate value iteration in the last lecture, and how we could convert approximate value iteration to empirical version. And that was a reasonable idea, more or less, and it's kind of the basis of many current methods, like DQN is based on that. So we also had some ideas or some methods based on starting from projected Bellman error. And we talked about a few ways we could use projected Bellman error in order to define algorithms for approximate value iteration. Some of them was based on direct solution of some linear system of equation, and some of them were based on converting that fixed point equation that comes from projected Bellman error or projected Bellman operator, and then define an iterative procedure. So now I'm going to talk about kind of the direct solution of it and get a method that is called least squares temporal difference learning. I mean, we had it before. I just want to have the empirical version of it. So we had different approaches to approximate V pi if we start from projected Bellman error. One of them was based on solving this equation of V being equal to projection of T pi V onto function space F according to some distribution mu. And then we said that, okay, let's focus on a linear function approximation. So we had V equal to some phi times W. So V of X is like phi transpose X times W. And then if we had n states, we can write this V as a vector of these for all capital N states. And this capital phi, which is an n times p matrix, times W, which is a p-dimensional vector. And then what we have here is then I showed how we can solve it. So we could get W of this method, the solution, which we call it sometimes a TD solution, as A inverse times B. A is a P times P matrix, and B was a vector, P-dimensional vector. And with A and B, which had this form, which A is like phi transpose times M times phi minus gamma P pi of phi. And M was essentially this diagonal matrix that we put mu in it. And mu was the distribution that we have here. So the distribution with respect to which we do the projection. Okay, is this clear so far? Or do you recall LSTD? Okay, so this is the case that we need, this is the kind of the population version of LSTD, which means that it's not data dependent, but it's assuming that we know the model. Why? Because we have this P here, and we have this R here. And these are not known in the context of reinforcement learning. So what we need to do is to convert these to using data dn, which is kind of these tuples of x reward and xi prime, and in order to estimate this A and B. So the idea of LSTD is basically try to approximate these things using some A hat and B hats, and then solve this, using that solve this equation approximately. So it would be, so that would be essential LSTD using data.
We don't know mu as well, right, Professor?
All right, yes, we don't know the mu either. Well, okay, no, depends. Like in one context, we say that we choose mu, and we say that if the states are distributed according to this distribution mu, what would be the solution? But another context is that, say, for example, you are saying that mu is the station distribution of a policy pi. So I don't know that. So if you recall, in some parts, not in LSTD, but next I say that suppose we have, instead of choose mu equal to rho pi, station distribution, and then I use notation D in order to say this case. So if this is rho pi is the distribution that we want, and we only know pi, but we don't know what station distribution it induces, we also wouldn't know this M or D. But we can also choose it ourselves. Okay. So now the idea is that how we can estimate these quantities. So this is some linear algebra. If we do some linear algebra and write Aij, the ith and jth elements of matrix A, so which would be phi transpose M, phi minus gamma P pi of phi. If we write it and notice that M is a diagonal matrix, so it's kind of, because of the structure of diagonal, it makes this multiplication to get a kind of nicer, simpler form. What we get is something like this. It would be a summation over M, which is going from 1 to n number of states, of phi transpose of I and M times mu of M. So I'm substituting capital M with mu. So this is the M term of it, times matrix phi minus gamma P pi phi M and jth term. So we can write this. This is not, this is of course maybe a bit more clear, but maybe not so much. But if we expand it more explicitly in terms of what the next state x and next state x prime, and expand this capital phi transpose I and M, and each of these elements in a kind of more explicit form, then we get a form like this, that A would be this matrix, that it would be summation over all states weighted by distribution mu of phi, which is a p times 1 vector. So I write it as p times 1, phi of x times phi of x minus gamma times the expected value of phi at the next state. So starting from x, we go to next state according to distribution p of pi, and then compute phi of x prime. So that would be the expected value of phi at next states, starting from state x. We compute the difference of phi of x minus this value, and the whole thing would be transposed. So it would become 1 times p matrix or vector. And then the whole thing would become phi p times 1 and 1 times p matrix. So the whole thing would be a p times p matrix that is weighted according to this distribution mu. So this would become p by p as we expected. So I guess you have to go through it to see why this is the form. But we can see that this A that is we are computing here is having that kind of this specific form. And we can write the same for B. So B vector would be weighted according to mu of what? Phi of x times r pi of x. So r pi of x is a value, scalar. Phi is a p times 1. So we weight phi, we multiply phi by the weight of the reward multiplied by the weight of the distribution mu, and that would be my rp by 1 vector matrix. So why do we talk about this, or why this form is useful? But before that, maybe I just look at the chat. Okay. Okay, so I think this is still related to the previous discussion. So it's about the variance of empirical Bellman operator applied to Q. So maybe I get back to it later if it is not resolved. Okay, so now that A and B are of these forms, how do you think we can estimate them? Like I give you data in form of, say, Dn is xi reward I, xi prime. So here, there's no action because this is kind of policy evaluation. Suppose we don't care about action. We want to estimate just value function. But underlying, maybe there's action is selected according to policy. So how can I form this A and B? Any idea? So what do we need in order to convert A or form empirical version of A, say?
So we can get a single sample, I guess it's a Monte Carlo estimate of A, right? Using Dn, or sorry, using one tuple from Dn.
Okay. So that's good. So let's try to write it. So instead of phi of x, okay, suppose I add this extra thing that xi's have distribution of mu. coming from distribution mu. So this A, this summation over x's according to mu is essentially saying that we are computing the expectation. When x's are coming from distribution mu. So I can substitute expectation with the empirical expectation or empirical average. So the result would be, instead of mu of x, or instead of phi of x, what if I just write phi of xi prime, right? And then maybe I can also write phi of xi here too. So what should I do with this term? Because I don't know p of pi.
Phi of xi prime.
Okay, so yeah, exactly. So I can write this whole thing as phi of xi prime. And there's a gamma there. So the whole thing I get would be phi of xi minus phi of xi prime transpose and then multiplied by this phi of x. And then mu of x I don't need to be worried about because x's are coming from that distribution. So this is somehow like, you can think of it, this A has two expectations. One expectation is over x, another expectation is over x prime. And I just replace both expectations with data. Like at x's, I choose xi's, and at x primes, I choose xi primes.
There should be a gamma there, right, Professor?
There should be gamma right there, right? Thanks. So that's the idea. And we can do the same for B. This x is coming from distribution mu, so I don't care. But I care because also x's are coming from mu, so I can substitute it with phi of xi, and then reward. Okay, I don't know r pi of x, but I have a sample from it, so I have ri from it. So that becomes ri here, because ri would be essentially a distribution, a sample from a distribution with R, capital R, pi condition xi, so distribution of reward at xi. So if I have a single sample from it, that would be unbiased estimate of it. So if we do all these things, so basically what I'm rewriting what we had in the previous slide, or after what I added to the slide. So given data points in the form of xi, ri, xi prime, with xi's coming from distribution mu, and xi prime coming from next states, and ri coming from distribution that's, okay, so maybe I should change it to be a bit more consistent. So there's no a prime here, but this is p pi of a condition xi. So policy is kind of absorbed in the transition kernel p, so, and that was p pi. And I guess the same here. So I can remove these things. So xi prime is coming from p pi of xi, and ri comes from r pi of xi. Then we can define empirical estimates of A and B. We call it A hat prime and B hat prime. Okay, so maybe I forgot this too. So A hat n would be essentially summation of 1 over n of phi of xi times phi of xi minus gamma phi of xi prime, this whole thing transposed. So it would be P by P matrix, and B would be the same as we had before, summation over 1 over I equal to 1 to n, the number of data points, of phi of xi times the reward that we get. And it can be shown that, so intuitively this should be unbiased, but we can also show that these are unbiased estimates. So expectation of A hat n is the same as A, and expectation B hat n is the same as B. Is this clear so far?
Can I ask a question?
Sure.
If you go back to the last slide, how does this kind of relate to maybe like a model-based approach where we would just have a separate, maybe function approximated estimate to p pi?
Okay, so you have a model that learns p pi and then use this model to estimate A's?
Right.
So you could actually do that. Like you could estimate, use data and estimate p hats pi of n. We haven't talked about how, but it's kind of clear. If it's a finite state, you can count how many times you have gone from state 1 to a state 10, say, and then you count it and divide it by the total number of times. So you get a kind of count-based estimate, which happens to be the maximum likelihood estimate for finite states problem. So you can compute that and then use this in order to compute A of, say, use this new notation, A of p hats pi, which basically is the same A here, but instead of gamma p pi, you substitute it with p hats pi. So if you do that, then you can solve LSTD in the population version with this kind of estimated model. And the kind of the interesting result is that the solution would be exactly the same as this. So this is, I think, a bit surprising, but it has been shown that it would be the same. So that's why we can say LSTD is implicitly building a model of the environment using data without actually building it. So the solution would be the same as doing population version of LSTD, but without constructing that p hats of pi explicitly.
It's the same in the discrete state space case, using counts?
Using counts, yes.
Okay. But I guess in the continuous case, it would depend on how you estimated the p hat pi.
Okay, that's right. I think there is. Yes, it depends on, of course, how you represent the value model, because you have to approximate if it's continuous. But there is a result that says if you use a special type of models for estimation, they're called linear expectation models, if I recall correctly. So I think it's called linear expectation. So they essentially use some kind of linear features in order to fit the model. There is some detail, but that's the idea. Doing that would be the same as doing LSTD with the same features that are defined to use the model. So if you use phi for LSTD for value function approximation, and use the same phi to define this linear expectation model, then the solution would be the same. So that's actually a kind of relatively recent result, like several, I guess LSTD came, I think late 90s, maybe 98, 99, LSTD came. And then the other method that I'm going to talk about, LSPI, in a few slides, that came, I think, in 2003. So this equivalence was figured out in 2000, maybe 9 or 8. So I can't remember the exact name of the paper, but one group was by with Sutton, Chaba-Sepeshwari, I think Alborz, Gerami-Fard, and Michael Bowling. So I think the paper is linear dyna. So I can't remember. I can't remember the order of authors, but it is rich. So it's a linear.
Is it dyna style planning with linear function approximation and
yes,
sweeping?
Yes, yes, yes. So it's, I think it's 2008 or 9, right?
Yeah, I think sometime around that, 2008. Yeah.
Yeah. Okay. And then the other one is by Ronald Parr and a few others. I can't remember the name of the paper, but that was the same year essentially. That they showed this kind of equivalence, which was nice. Okay, so yeah, thanks for the link. Okay, so yes, so this is kind of interesting because there is this connection between LSTD and model-based approaches, that they are implicitly building a model. And I have this comment later, but let's mention it. LSTD is considered as a kind of a sample efficient method compared to, say, TD-based methods. Maybe we haven't got TD-based method in the with function approximation yet, but with like finite state, discrete states and actions, we had seen it, like Q learning, different TD methods. Those are not very sample efficient because they process data and throw it away in some sense. And they update the value function a little bit. But LSTD essentially collects all data and use all of them, kind of squeeze all information from them. So it is sample efficient. And I guess maybe one kind of another viewpoint is that because it builds a model and then solves the problem exactly using that estimated model. So yes, so these are properties of LSTD, and maybe one other comment is that if xi's are independent, so here xi's are coming from distribution mu, but they are, if they are independent too, then by the law of large number, A hat n converges to A, and B hat n converges to B. We don't, of course, need to have independence. Like we have law of large number with, say, for Markov chains under some regularity condition. So even if xi is coming from following a policy and generating a Markov chain, we still get estimates of A hat n's that converge to A. Of course, without any assumption, we don't have that convergence. So for example, if I have xi, yeah, I can think of kind of nice construction, but you can think of very dependent construction, or construction that generates xi's in a very dependent way, that you don't get a nice convergence to what you want. But that's it.
Professor, can you mention again what you mean by implicitly building the model?
Sure. So by implicitly building a model, so here I guess the idea was that, so is this clear? Like we get the n, we build a model, and then we get this A of p hat of pi, and then we solve for it using, just plug it in this equation A.
Yeah.
So this is building model, right? Now, okay. So the kind of the claim is that the solution of that would be the same as the solution of solving LSTD. So LSTD is not building it like if I compute A hat n this way, the solution that I would get would be the exact the same as the case that I'm building a model explicitly.
Okay, thank you.
So in that sense, it is building it implicitly because it is getting to this exact same solution.
Mm-hmm. If you're going to do the pi thing, right, first.
Yeah, p hat of pi thing, yes.
Yeah.
Okay. So, so another comment about LSTD is that we can use LSTD to estimate the action value function Q pi 2. So it would be very similar. It wouldn't be much different. So the only difference is that we need to define features like fees that are function of both states and action instead of only states. And if we can do that, which we can, then we can get LSTD that estimates Q function. And so I think this was introduced by Ronald Parr and Blagoudakis and Parr in 2003. So that's LSPI paper, and they call it LSTDQ method. But because I think the principles are basically the same, I call both of them LSTD. So it's okay to call them LSTD, even though the original LSTD was only called for estimation of V, not Q. Okay, now we have LSTD. So this is for policy evaluation. So if we have a policy, we can use LSTD to estimate V or Q, and then that's the approximation of the policy. But we can also use put this policy evaluation step within a policy iteration procedure in order to find a new policy and potentially better policy, so that we gradually get closer and closer to the optimal policy, or at least approximately. So we can use LSTD to define an approximate policy iteration. So we call it API usually, to obtain a close to optimal policy. Now we don't necessarily get to optimal because there are approximation. So this is essentially with the policy iteration algorithm that uses LSTD to evaluate a policy, and it is approximate because of the use of function approximation and finite number of data points. So then the results, like we had in policy iteration, we had this result that policy iteration converges to say optimal policy in a finite number of iterations. So we had two results on that, like one was better than the other one. So those results do not necessarily hold exactly. We may not converge to optimal policy, and even we may not converge to any single policy. So it has been observed that approximate policy iteration may oscillate in a sense that so maybe I just write the performance. Well, maybe I should describe the method first, like how it looks like, and then I describe how it behaves. So this is kind of like a minimum of how LSPI looks like. So we get a data points. Oops, there is an error here. So this should be Ri and Xi prime, reward and next state. So I think I copied it from somewhere else. So, oops, so here, okay. Sorry about this. This goes away too. So that's hopefully the last error. So we have a data set of state action, reward, next state, and we start from some initial policy. And then for capital K iteration, we compute LSTD using data that is given and policy pi k in order to approximately evaluate policy pi k. So that would be Q hat of pi k. And then we do policy improvement step, which is basically just choose the greedy policy with respect to this recent Q hat of pi k in order to get a new policy, pi k plus 1. And then at the next step, I put it here I evaluate this pi of k plus 1 with the same data sets using LSTD, and then repeat this for several iterations. And if we write it in the LSTDQ formulation, you can see that just given a set of data sets, fixed data set, is enough in order to compute Q essentially. So LSTD for action value function would be an off-policy method. So with a given data set, I can evaluate any policy. Of course, the quality of how well I can evaluate it depends on how close the data distribution is to the distribution of, say, induced by that policy. But in principle, I can compute it. So this is this kind of the basic of LSPI. Is there any questions so far? Okay, few comments. We may also collect more data during LSPI. So the way I described it is just data is collected once, so it's a batch method, and then I gradually improve it. But I can gradually increase, or maybe increase my data sets by, say, following the policy that I obtained at iteration k, collect more data, and then add it to the previous data set, or maybe replace it with the previous data set, and then basically run LSTD with this updated data set. So we can collect more data during LSPI. LSTD for action value function Q is an off-policy method, and it can evaluate any policy that is different from the one that is collecting data. The other comment is that LSTD and LSPI are considered sample efficient methods compared to, say, TD-based methods. So they use data, they store all data, and they use it in kind of better way. And there are some kind of theoretical results showing that what is the converged sample complexity of these results. But I'm not going to talk about that. But then the one issue, potential issue of LSTD and LSPI is that it is not computationally cheap. So it is not computationally cheap because it requires a matrix inversion. So we had this matrix inversion here. So if matrix P A is P by P, if we do it naively, it would be P to the power of 3, order of computation. So order of that computation is P cubed. And if you want to do it online, like, so what I described was an online method. Data was collected, I compute A once and inverse it once at each iteration. But then if I do it online, like I collect one data point, I construct a new A, and then take inverse of it, then that would be computationally very expensive. Like if I have n data points, at each iteration, I need to do a P cubed computation, so it would be n P cubed, which might be large if P is large. So if it's P is like 10, 100, 1,000, that's okay. But if 100,000, no. But then there are ways in order to do the compute the inverse in an incremental way. So there is this Sherman-Morrison formula that we can compute A incrementally based on the previously inverted matrix A hat of inverse at step n-1 at the previous step. And the order of computation becomes P squared instead of P cubed at each iteration. So this is better. I'm going to talk about this Sherman-Morrison later, but not in LSTD case. Okay, any questions so far? I may need to go a few minutes out of time to finish it, this lecture, but shouldn't be too long. Like, this is the last section. It's not going to be very.
Professor,
Sure.
LSTD is using the direct solution.
Right.
What is there, like sort of an LSTD type of thing where for policy iteration you use the finite sort of that iteration of the iteration methods that we use to find the solution rather than the direct solution?
Yes, and actually we are going to see that next.
Okay.
So LSTD was direct solution for computing the projected Bellman error.
Yeah.
So here I'm going to see methods. So that's a good point. So I'm going to show methods that use iterative methods for computation, because we had two methods, if you recall, from several slides ago. Okay, here I'm talking about online methods with function approximation. So we have seen online methods like TD methods that agent updates a value function as it interacts with the environment. Of course, the difference between online methods and batch methods is kind of blurry, because we could run LSTD in an online way too. So nothing prevents us to compute it as we collect new data, update A and B, A hat and B hat. But I put it separately. So now about online methods. We had this projected Bellman operator, and we said that we can consider it as a fixed point equation, or try to find a fixed point solution for it using an iterative method. And we had two methods, which were defined based on they were population version of methods, so they required the knowledge of, say, transition model. Now I want to convert them to a sample-based one. So one thing is that when we designed it to somehow like be similar to a stochastic approximation method, even though there was nothing stochastic in those forms. So one of the methods was this. So we had this rate update, I'm just copying, that WK plus 1, so this is linear function approximation. So W weight of linear function approximation between 1 minus alpha times WK plus learning rate alpha times this matrix phi transpose d pi phi, the whole thing inverse. And remember that d pi was the stationary distribution, is defined based on stationary distribution of policy pi. So d pi is a diagonal matrix of rho pi, which is stationary distribution of pi. So we have phi transpose d pi phi inverse, and then we have phi transpose d pi times reward r pi plus gamma p pi phi times WK. So this kind of long formula. And you know, if we have, say, P, and if we have R, and if we know the station distribution, then we can compute this thing and compute WKs. And we had this thing because we showed this is a kind of, it has a contraction property if and converges to the fixed point solution of projected Bellman operator, which is the same as what, say, LSTD finds essentially. LSTD finds it through direct method by taking inversion. This is through iterative process. So now what we want to do is that make an online method out of this, and in order to, in a form of a stochastic approximation procedure, and we need to, in order to do it, we essentially need to find a way to estimate these quantities, like first phi transpose d pi phi, this one, and then the second term. So if you estimate these online, then everything should be fine. We can do computations online. Is this clear? Any question? Okay, so this is the first method. So let's just try to find what each of those terms are actually computing, and then try to replace them with the empirical version. So the term phi transpose d pi phi, we can write it as essentially summation over all states of rho pi of x, the probability of being at state x according to station distribution, of phi of x and phi transpose of x. So this is p by 1, this is 1 by p, so the whole thing would be p by p matrix. And in another form, we can write in an expectation, which may make it even more clear that this is expectation of phi x phi transpose of x when x is coming from station distribution. So that's great because we know how to convert an expectation to its empirical version. So if we have, say, t data points, t data points x1 to xt, with xi's, each of them coming from station distribution of pi, we can estimate it by matrix A hat just by computing the average over them. So it would be A hat of t would be 1 over t of summation of I from 1 to t of phi of xi and phi transpose of xi. So, and then this matrix is an unbiased estimate of the expectation, and then under usual conditions for convergence of law of large number, it converges to A. So this, under conditions, it converges to A. So if, say, xi's are independently selected, that converges. If they're coming from Markov chain, if chain has some is a nice chain, it's not strange Markov chain, then we have still we again have a law of large number. So I guess one thing is that I use t here instead of n to kind of emphasize that we want to talk about like online methods. So I use t for online methods, n for batch methods. I try to be consistent, but probably I made some mistakes here and there. Okay, so this is A hat for estimation of the other, and okay, so just don't confuse this A with the A of LSTD. There are two different matrices, but I just use the same A matrix for it. So for the other term, we have phi transpose d pi r pi plus gamma p pi phi wk. So this is very similar to just Bellman. This came from applying Bellman operator to value function. And if we write this, we can see this would be summation over x's of rho of pi of x, probability of being at state x according to probability stationary distribution of phi of x, okay, phi of x times r pi of x plus gamma times essentially phi transpose x prime of w when x prime comes from next state distribution. So this is essentially, these two terms is the value function at the next states. Here I'm computing the value function, expected value function at the next states. I'm adding reward here. And there's this gamma factor too. So this is essentially t pi of v when v is a linear function approximation. So if xt is coming from rho pi and xi prime coming from the next states, and the same for reward, then the random variable that is constructed by just having phi of xt times rt plus times the whole parenthesis of rt plus gamma phi transpose phi of x prime of t transpose times w, that would be an unbiased estimate of what we have above. So this is the expectation. 37 is expectation. This random variable is an unbiased estimate of it. Okay, is this any question? Okay, so this is great because, I mean, we designed or we had stochastic approximation methods that can work Well, when we feed them noisy version of something, like unbiased version of some quantity. If we, with stochastic approximation, if we set the learning rate properly, then they would converge to the expectation of that noisy quantity that we want. So here we have this dynamical system that is deterministic. We converted it to a noisy version of it. And what we would get would be something like this. That stochastic approximation version of it would be that each time step, like as agent is interacting with the environment, after observing xt, rt, xi prime t, updates the weight from wt to wt plus 1 by computing this quantity, like 1 minus alpha t of wt plus alpha t of a inverse, a hat t inverse, times phi of x t times rt plus gamma phi of x prime of t transpose times w. So this would be the value function based on one sum. And at can be also, we can also update at incrementally, because at was essentially at would be, can be written as 1 over t. It's the summation of 1 from I equal to 1 to t. So we can write it as 1 over t times t minus 1 times a hat of t minus 1 plus the new data, which is phi of xt, phi transpose of xt. And then this would become essentially these two quantities. So we can update a incrementally. And we can also compute the inverse of it incrementally, which, okay, so here, I mean, I show you how to compute it a incrementally, but you still need to compute the inverse of it, but which is computationally expensive. So it's order of p cubed or a bit better. But then we can do it incrementally using Sherman-Morrison formula, which I mentioned at LSTD. So what is that formula? It's a kind of saying that if we have a matrix A, so it's a general A, and we have two vectors, so A is d by d, vectors u and v are d-dimensional, and then the first claim is that matrix A plus uv transpose is invertible if some condition holds. Let's get back to this later. And if it is invertible, then we can compute it like this, that inverse of A plus uv transpose in the whole thing inverse. So, and notice that uv transpose is d by d matrix. So it would be a rank 1 d by d matrix. So we are adding a d by d matrix to A. So the inverse of it can be written as inverse of A plus this quantity, which is A inverse times U and V transpose times A inverse, divided by 1 plus V transpose A inverse U. So if you check the dimensions, you see that the denominator is a scalar. So it would be like, so it would be 1 by d is v, then we have d by d, and then we have d by 1, so it would be 1 by 1 matrix. But here, so we have A, so we can do this computation easier because we just need to compute, first we can compute matrix A times vector U. So this is a matrix vector product, so we can compute it with the order of p squared. And then we have another, so that would be, okay, so this is p by p times p by 1, so the whole thing would become p by 1. And then we have v 1 by p matrix from v transpose A inverse. So that would be p by p matrix. But this p by p matrix has a nice structure because it's like outer product of two p-dimensional vectors. And sorry, here I should have talked about P. Everything is D here. So P is D. Okay, so we can use this formula in order to compute our inverse. So we can do this computation with the cost of P squared, and then we can get a new inverse of A based on the previous inverse. So this is just a method that shows that this is kind of computationally better than being cubed, P to the power of 3.
Professor?
Yeah.
So, I mean, all of these methods, aside from the second value iteration method, they all imply that the matrix A is invertible. I mean, when you're doing these kinds of things, do you have to check whether it's invertible when you're doing it? I guess when you're implementing it, or no?
When you implement it, the way that you usually do is you usually add some maybe regularizer in order to make it invertible. Like for LSTD, instead of computing, okay, let's see if I can. So here, so for example, to make it invertible, you add some epsilon I to it. So what we know is that like A, if n is large, like the number of data points is large, then A, okay, so better to say, A is invertible matrix. And n, when n becomes large, a hat of n becomes invertible because it's converging to it. But at the beginning, if you have only, say, 10 data points, then it wouldn't be invertible. So usually people, what they do is adding some term like this to numerically stabilize it.
Okay.
So that's the idea.
And that's at the beginning, right? Not, I guess it goes through, I mean, I guess depending on the number of data points.
Yes. Yeah, I guess one thing you can do, yeah, so either you can make epsilon go to 0, or the way you can do it is that instead of having a 1 over n here, you remove 1 over n, you just have summation, but add a constant epsilon plus I in the beginning. And then you gradually update it. So the effect of this summation term gradually becomes bigger and bigger because you're adding more terms to it. So it's not normalized. So in that case, this would be equivalent of having 1 over n there, but having epsilon over n instead of this term.
Okay.
Okay, so this is one method. Okay, some comments is that matrix vector multiplication is order of p squared. So per sample computation cost of that update is p squared again. So if we compare it with TD method for finite state and action problems, where we use a kind of table lookup to represent value function. So the order computation order of it was order 1. So which essentially needed to look at the value, change it with that state, and that would be all. So that would be order 1. So this is order p squared, which is much larger. But maybe this is not exactly the fair comparison because the computational cost of value function itself for finite state problem is very different from the computation of value function when we use, say, linear function approximation. When we have linear function approximation, the computational cost of just computing the value function is order p itself. P features, so the computation cost would be order p. Whereas in the case of table lookup, it would be order 1. So maybe a better baseline to compute the methods is that to compare the cost of update per time step with the cost of the ratio of it with the cost of computation of V for a single state. So it's kind of how much, in order to do the update for V, how much more computation I need to do compared to just evaluating V. So this would be computational cost of update per sample divided by computational cost of computing the value of a single state. So for TD, this is again order 1 because both of them are order 1. Both of this would be order 1, but for method 30 that I had in these slides, the order would be P. Like the computation here would be P squared, the update computation, but the evaluation of value function would be order P. So the whole thing would be order P. So this is much better. This shows that the computational ratio increases as linearly as the number of features increases, which is maybe okay, but this is maybe not ideal. Like if P is a very large number, 10 millions, then that's going to be kind of substantial extra computation compared to TD methods for finite state problems. Oops, okay. So hopefully it lasts. Okay, so maybe I should just mention this method that I mentioned, this is not very standard method. Probably someone has thought about it and analyzed it, but I'm not sure like what is the result about it. So we know the convergence for deterministic case, we proved it, but for stochastic case, I'm not sure if anyone has proved its convergence or not. I believe it should converge, but this is not, I don't know if there's a proof for it or not. So that's a kind of non-standard method, but seems to be a kind of nice one. So the second method, so this would be, I guess, almost done. Yeah. So this would be the TD method with linear function approximation, and this is based on the second method that we had for finding a fixed point of projected Bellman equation. So the update rule that we had, the population version was WK plus 1 would be WK plus alpha times D of essentially RP plus R pi plus gamma P pi phi WK minus phi WK. So this was essentially Bellman residual, a value function which is using linear function approximation. So this is Bellman residual. So we have a Bellman residual, we multiply it by d pi, and then that would be our update. So we go through the same procedure. If we convert this to an empirical version, so if xt is from station distribution, xi primes the next state reward is the same, then the random variable that is defined as phi of xt plus rt plus gamma phi transpose x prime w minus phi of xtw. So this is essentially a single sampled version of Bellman residual. Then this would be our this would be an unbiased estimate of this quantity above. So this would be unbiased estimate of it. We can also write this term, this sample-based Bellman residual. We had called it TD error, so that would be delta of t, which would be, again, exactly this thing. So we can write this random variable in a more compact way as phi of xt times wt. So that's great. So we have an unbiased estimate of that quantity. So we can think of a stochastic approximation procedure in order to convert to estimate it. So stochastic approximation procedure would be like this, that WK plus 1 would be WK plus learning rate, or step size, times phi of xt times TD error. And this would be the TD error, TD learning with linear function approximation. So this is now standard. This is something like, say, if you go and look at the Sutton and Bartu's book, that would be the TD error with linear function approximation. Okay, so a few comments. Okay, so the population version of this update rule, so the population version of it, under when X coming from station distribution converges. And we had it, I think we have it in lecture notes. So we don't show it for stochastic approximation version of it. So we know that the deterministic part converges to the true value, but what about the stochastic part? This is, but we might suspect that this should converge to. So because it is essentially following a noise contaminated version of a dynamical system which is stable or convergent. So the deterministic part is stable. Now we're just adding noise, and adding noise should not change the convergence property very much, especially if we choose, well, if we choose learning rate properly. So if proper choice of step size sequence, then we can expect convergence. And then this is in fact true. This was shown in '97 by John Tsitsiklis and Benjamin Van Roy. So that's kind of considered as a kind of one of the seminal papers and important papers in RL, that they prove that linear TD with linear function approximation converges. Few comments is that the convergence holds only when samples come from station distribution of pi. So if you sample from another distribution, say distribution mu, which is different from rho pi, but you're still evaluating policy pi, you may not converge. And actually it might diverge. So linear function approximation, TD with linear function approximation, if the distribution is not the distribution of the policy you're evaluating, might diverge, which means that this is, and if you compare it with, say, the finite state case, we had much relaxed conditions for convergence. We converge there if we visited each state infinitely often. But here, actually, the distribution of visiting those states should be the same distribution of policy we are evaluating. I mean, this does not mean that if you run it with another distribution, it always diverge. Probably in most cases it doesn't diverge, but it might diverge. So a consequence of this is that if you use Q learning with linear function approximation, it might diverge, because Q learning, the policy it is evaluating is greedy policy with respect to current estimate of the value function, right? So it was a greedy policy with respect to Qt. But that policy is very likely different from the policy that you're following to generating data. Because, for example, you're following epsilon greedy policy to have enough exploration. This mismatch between policy you're evaluating and policy that you're following, which is called behavior policy, may lead to divergence of Q learning. So people tried a lot to prove that, well, basically, yes, I guess there are counterexamples that shows that Q learning diverges. So this doesn't work. And there are a lot of work that try to change Q learning update to have something like Q learning, but non-divergent version of it, but with function approximation. And maybe one comment is that, like, you can think of it fitted Q iteration or approximate value iteration that I mentioned in batch method somehow solve that problem. But there are still conditions for them for convergence of them. They are not guaranteed to converge if we don't choose, say, the data distribution properly, or say, choose function approximation in a wrong way. But maybe I guess that's a kind of interesting point that, say, if you use Q learning update with the deep neural network, it would not be as stable as doing DQN, which is more like fitted Q iteration, approximate value iteration. So doing approximate value iteration makes things a bit more stable. So this stability is an issue, especially when we want to compute, we want to do off-policy methods, where, say, do something like Q learning. Okay, so I try to go through this quickly. So we can do Q learning or TD learning to estimate the action value function Q pi. So this is not Q learning, just TD, but evaluating action value function pi. We just use phi of XA transpose W. So features are now a function of both state and action in order to represent the value function. And then we can have update rule like this with TD error, which looks like that, which is essentially the same, except that we bring actions in order to kind of get a TD update rule for estimation of Q pi in an online way. And this works again, so there's no problem here. And so we may use something like this to compute SARSA-like and Q learning, right, algorithm. So for SARSA, the procedure would be very similar, but just actions AT should be pi of, so essentially we have this tuple of XT, AT, RT, X prime T, and A prime T. So remember that this is called SARSA because this is SA, R, SA, if we use S. So that would be SARSA. So AT would be coming from policy at state XT. A prime T comes from the policy at next states. Or here maybe it's better to, I don't use T, X of T plus 1, so I'm using, so X prime of T. But in practice, in many cases, it would be a trajectory. So everything would be similar, and the update rule would be the same with a TD error, which is in the form of reward plus gamma times phi of X prime of T, A prime of T, the whole thing transpose times WT, minus phi of XT, AT transpose WT. So that's with the SARSA algorithm. And we can do the same thing for Q learning, except that we have the max over actions here, but the rest would be the same. So the point here is that, as I mentioned, the policy that the agent is following, the behavior policy, is usually different from the greedy policy with respect to QT. So for example, agent is following epsilon greedy policy with respect to QT, but what is being evaluated is the greedy policy. So this means that the policy being evaluated may not be the same as policy generating data, which makes it an off-policy sampling scenario. We had seen it before with this, we said even in finite state action case, Q learning is an off-policy method. And it doesn't matter if it's finite or not. The result, as I mentioned, is that the convergence guarantee for TD with linear function approximation does not hold here anymore. And Q learning with linear function approximation might diverge. Okay, so that's, let me just check this. If you want to go, I don't want to keep you here because we're already 25 minutes after, but this would be last part, so it will be recorded and you can see it. You can watch it later. So I want to talk about some other viewpoint of these TD methods, which is, it can be called semi-gradient viewpoint or pseudo-gradient viewpoint, for the reason I'm going to explain soon. So the way we started was essentially we started from let's say linear. The way we motivated TD method with linear function approximation was saying that, okay, we start from this fixed point of the projected Bellman operator, and then we plug it there and then devise an iterative stochastic approximation method. And there were two ways for doing it, or I showed two ways for it. But then the question is that why can't we do something like stochastic gradient descent, which is like procedure that people in all machine learning are using to, especially supervised learning, to minimize their loss functions. Can we define a loss function and then derive some SGD-like type of method for our reinforcement learning update? So this viewpoint, okay, so let's go back to the very simple case that is, we assume that we know VPy, we know the true VPy, somehow someone gave it to us. And then we want to find an approximation we had. So this is what we had, I guess, in last lecture when we talked about Monte Carlo estimation. So instead of VPy, we had noisy version of it, the return. So the population loss would be like this. So maybe I put it squared here. The loss wouldn't be, the solution would be the same, whether it's squared or not, but for the next step, I need squared. So arg mean of, say, half of norm of VPy minus V hat of W with L2 norm according to distribution U. So we can have that. So if this is the population loss, we can, the way that we get SGD is that we take gradient of it, and then we replace expectation with samples, and that would be SGD. So using samples XT coming from mu, we can define a SGD procedure that updates WT as this way. So WT plus 1 would become WT plus minus alpha T of gradient of the loss function with respect to W, right? So if we do this, so what we get is that it becomes plus alpha T times VPy minus V hat evaluated at XT. So this is kind of the residual term, how far we are from the goal. And then this is the gradient term, gradient of V hat with respect to W when evaluated at WT. So we compute the gradients, multiply it by the residual, and move in that direction. And if alpha T's are selected properly, then the stochastic gradient descent converges to the stationary point of the objective, the loss function. And then if we use a linear function approximation, so things become, what happens is that the loss function becomes convex. So if I use, say, phi transpose X W here, so I would have terms like this. This would be convex as a function of W. You can verify it easily. So means that the global minimum is unique. So if I choose parameter step size or learning rates properly, then WT converges to the global minimum of the objective. And then here, is this clear so far? Let's see how much I have. 8%. Any question? Okay. So this is usual supervised learning. Just instead of target, I use VPy. So VPy acts like target in the supervised learning sense. So this is like regression. You're solving regression problem with SGD. But we don't have VPy, which usually the case. Like we want to have a method that works without knowing VPy. So we may use something called Bootstrap Estimate instead, which is essentially using the empirical Bellman operator. So T hat of pi of Vt, which would be RT plus gamma V of T of X prime at T, which also I can write this Vt, it's a function of W weights. So I write it as V hat of XT and WT. So that would be my target. So instead of VPy that I had in previous slides, so instead of VPy here, I put this reward plus gamma v of next state there. So that would be the instead of that. And then the rest would be the same. So this is called bootstrap estimation. I can't remember if I mentioned it or not, but bootstrapping means in this RL context, but not in statistics, means that we use our current estimates of something in order to have a better estimate, and replacing the current estimate instead of the kind of the target value. So I don't have V pi, but I can use my current estimate of V in order to, say, define T pi of V hats. And I know that this T pi of V hat kind of somehow is closer to V pi than the current V hats. So doing these things is called bootstrapping. Okay, so this is fine. We can do this. And if we have a linear function approximation, so we have V hat in the form of phi transpose W, the update rule becomes, if I replace there, so it becomes, okay, the gradient part. So we have this gradient here with respect to W. So this becomes phi of xt essentially. So this is the gradient. Then the residual part would be as before. And probably you recognize that this residual part is simply the TD error. So I can write it as WT plus 1 would be WT plus alpha T delta T, the TD error, times phi of xt. Okay? So now the point is that this is exactly the same as TD update that we had several slides ago. So the second approach, the stochastic approximation version of it, gets to exactly the same points. Here, except that we started from doing something like a loss function, taking stochastic gradient descent of it, but we don't know V pi, so we replace V pi with reward plus gamma V hats. So essentially the empirical Bellman operator version of it instead of V pi. And then the result would be the same as what we get here, we got before in TD learning. Okay? So one important point here is that we did one step in a kind of heuristic way or hand wavy way. And what was that step? That step was when we replaced V pi, this step. We don't know V pi, so we replaced it with T hat pi of Vt. So why did we do that? I mean, it turned out to be okay, like we get the same TD. But this would not be equivalent of doing stochastic gradient descent of any loss function. Because the loss function that we started was this one, like it had a VP. And then we took the gradient of it, and we got to this, say, term 1 and term 2. And only we replaced V pi here with our bootstrapped estimate. So one question is, you may ask, okay, so what would happen if instead of V pi in the target, which we don't know, we have something like that reward plus gamma V of next state there and start from different objective and then do SGD for that. But maybe before doing that, I just want to say that here, so TD update is not a true SGD update because it is not a SGD of any loss function. There is a kind of one step of jump there, or heuristic reasoning that does not come from following SGD. That's why it's called semi-gradient method. So because it's not exactly gradient method. Again, it would work if it would converge to what we want if the samples come from station distribution of that policy. But if the samples are not coming from station distribution of that policy, the TD procedure might diverge. But if it was SGD method, it was like following a real loss function and followed that, it would not diverge as long as the step size are chosen properly. So that would be kind of the difference. Like if it was a true SGD method, it would not diverge. But now that it's just a kind of semi-gradient type of method, it might diverge if the distribution is not right, is not station distribution. Okay, going back to kind of possible question that what happens if we perform SGD on, instead of having V pi here, which we had before, sorry, not here. So previously we had V pi here, but now let's substitute V pi with T hat pi of V hat with parameter W evaluated xt. So this is just for one sample. And then we can compute its gradient. Like now let's do SGD on this objective. So we can write the SGD with this objective. So it is just, okay, we have this residual term, which looks, this is similar to what we had in, it's the same as the residual in the TD method. So this would be essentially the minus of TD error. But then the gradient here, you notice that the gradient is with respect to both terms, right? Because V hat appears in both terms. So we have gradient with respect to W of V hat minus gradient of T hat pi of V hat. And if we write this, so the second terms becomes minus gamma times gradient of V hat at X T prime, the next state, with the same W. So this is gradient of value function at the next state, and the difference between these two. Okay? Okay, so this is a legitimate SGD update. And if we do it with linear function approximation, I just substitute, the gradient would change, TD would be the same. So I get the update would be WT plus 1 would becomes WT minus alpha T delta T TD error times phi of xt minus gamma phi of x T prime at the next state. So this is similar to TD update, except that in TD update, instead of having these two terms, we would have here phi of xt. So the second term is not there. So, I mean, this doesn't look a big deal. It's a small change. But the effect of it is that this is similar. This becomes essentially the same as Bellman residual minimization, or the empirical version of the Bellman residual minimization. And the loss function, as I argued earlier today, would be biased. So if you update this thing, like SGD, that would be a stable system, stable learning procedure. It converges to something. But the point that it converges would not be the minimizer of the Bellman error. So that's the issue with it. That's why we don't often use it. I mean, this is a method, but it has this issue with it. Okay, so maybe one other comment is that there are these methods called gradient temporal difference learning. They call it GTD, and there are several variations of it, which are essentially going back to one of the earlier formulations, the optimization-based formulation of finding the fixed point of the projected Bellman error. So instead of trying to solve a fixed point equation, say, which we had here, they try to solve, this is, I add a new here. They try to solve this optimization problem in an online fashion. And there are different ways to do it. and I'm not going to talk about it. So I think Sutton and Bartow's book has a good section on it. So that might be good to take a look at it. I may add it to lecture notes at some point, but probably not so soon. So these are very good methods in the sense that they are stable. They don't diverge because they're essentially some form of, you can think of it almost like a SGD type of method. They're minimizing a loss function instead of trying to find a fixed point. So they have a nicer convergence properties compared to TD methods for linear function approximation. And these are kind of, the development of it was a kind of big deal. Right, yes, so I maybe just add that using this loss function, the designing algorithm in this loss function has been kind of explored first in the batch RL setting. So there was a paper, I think, by Andras Antos, Remy Muno, and Csaba Szepeswar in 2008. And then I was working on regularized version of them. So it would regularize LSTD, which used this loss function. And then afterwards, we had these online methods that does this computation in online fashion using the same objective function. And they became these gradient temporal difference learning methods, and they came like a few months later. Okay, so just a summary. So this was a very long lecture. So I think this is our fourth time that we are going through this lecture, fourth session. But value function approximation is a big part of RL, so it's good to focus on it. So what we did was basically we argued that function approximation is needed for large problems, either large finite states like millions or billions, or when we have a continuous state space. Then there are several approaches for approximating the value function in the population sense. So we had a direct estimate, we had Bellman error minimization, and projected Bellman error. Then we talked about batch methods. So we talked about approximate value iteration, fitted Q iteration, LSTD, and also BRM. Talked about BRM as a batch method. And then with just earlier today, we went through these online RL methods. And so one of them was TD learning with linear function approximation. That was the second method that I described, which has like, we can get it from fixed point iteration procedure, or we can get it as a pseudo or semi-gradient type of method. And also we had this TD-like update, the first method that I explained, which is less standard. But we could get it easily from like trying to solve the fixed point equation. Okay, so next time I'm going to talk about policy search methods, especially policy gradient type of methods. And these are methods that try to estimate, they explicitly parameterize the policy. Here we haven't explicitly parameterized the policy, we parameterize the value function. But those methods parameterize the policy with some vector, say W, and then try to search in that space of policies parameterized by W in order to maximize the performance, which would be again similar to what we do, like expected return. They want to maximize it with some small differences that I'm going to discuss. And policy search method, so we will only have, I think, one lecture on it. But I'm going to introduce some papers for more recent advances in policy search methods. They have been quite a hot topic recently in the past several years because of some nice properties they have. Especially they are easy to work with continuous action spaces. Okay, I think that's enough. Is there any question?